I am going to deliver my presentation on crowns and crypts. Crown ethers are cyclic compounds in which a ring is formed by several ether groups. These are a special class of complexing ligands. Here I am showing the structure of 18 crown 6, 15 crown 5, 12 crown 4. 15 crown 5 is a liquid compound. Now, where they are so called? The term crown refers to the resemblance between the structure of a crown ether bound to a cation and a crown sitting on a person's head. In 1967, Charles Pedersen tried to prepare alkyl phenolic ethers. Fortunately, the reaction mixture contained some catechol. He was surprised to isolate a byproduct which was nothing but dibenzo 18 crown 6. Actually, the paper of Charles Pedersen, namely cyclic polyethers and their complexes with metal salts, became known to the colleagues simply as the blockbuster. Actually, the lithium, sodium, potassium, rubidium and cesium alkali metals can form the complexes. The order of stabilities of the complexes is lithium greater than sodium, greater than potassium, greater than rubidium, greater than cesium. Crowns and crypts have the unusual property to form stable complexes with all alkali metals. The exceptional stability has been attributed to the close fitting of the alkali metal ion in the hole at the center of the ligand. The formation of macrocyclic rings is favored by the presence of a cation of appropriate size that can serve to hold the partially formed ligand in position as the remainder of the ring is synthesized. A particular complex of choice can therefore be prepared in higher yields in the presence of an alkali metal which is selective for that particular macrocycles. It is the solid state structure of dibenzo 18 crown 6 which bonds with potassium ion. The most common and most important cryptand is 110 diaza 4 7 13 16 21 24 hexaoxabicyclo 888 hexacosane. Now we are going to alkalides. When sodium is reacted with crypt 222, then it forms sodium crypt 222 plus ion and plus sodium minus ion. The compound is supposed to be formed by shifting the disproportion equilibrium to the right hand side. Although it is endothermic by about 438 kJ per mole. The high lattice energy of the sodium crypt complex is the actual reason. The stability of sodium minus ion is due to the shielding effect of the cryptate on the cation, where the large ligand completely isolates the former. The electron transfer from sodium minus ion to sodium plus ion is thus prevented. This is the structure of electrolyte, where it is actually cesium 18 crown 6 plus electron, where cesium plus is the green sphere and electrolyte anion is pink. The electrolyte anions cannot scatter X-rays. The structure of the 18 crown 6 plus electron shows only the complex metal cation and no anions. The presence of cavities of radius approx 240 picometer formed by the complexed metal ion indicates the possible location of the electrons. Applications. Crown ethers are of enormous interest and importance in chemistry, biochemistry, material science, catalysis, separation, transport, and encapsulated process, where as well as in the design and synthesis of various synthetic systems with specific properties, diverse capabilities, and programmable functions. The solubility of alkali metal salts in organic media can be promoted using Crown's Crypts due to the presence of large hydrophobic organic ring in the ligand. KOH and KMNO4 can be used as an alkali and an oxidizing agent respectively in organic media. Now, gentle salts. A number of gentle salts containing alkali metal cation and gentle anions like T32 minus, Sb7 3 minus, Bi3 3 minus, SN9 4 minus have been prepared with the help of Crowns and Crypts in anhydrous solvent. Now we are going to phase transfer catalysis. Phase transfer agents promote the solubility of ionic substances in nonpolar solvents. They transfer the ionic substance from an aqueous phase to a non-aqueous one. Phase transfer agents increase the rates of reactions involving anions. The anion is relatively unsolvated and very reactive in nonpolar media compared to water or alcohol. Quaternary ammonium salts are most common phase transfer catalysts. Here I am showing methyl trioctyl ammonium chloride, which is a PTC. Again, it is benzyl triethyl ammonium chloride. It is also a phase transfer catalyst. In chemistry, a phase transfer catalyst is a catalyst that facilitates the migration of a reactant from one phase into another phase where reaction occurs. Phase transfer catalysis is a special form of heterogeneous catalysis. Ionic reactants are often soluble in an aqueous phase but insoluble in an organic phase in the absence of phase transfer catalyst. By using a PTC process, one can achieve phase transfer reactions, obtain higher conversion or yields, make fewer byproducts, eliminate the need for expensive or dangerous solvents that will dissolve all the reactants in one phase, eliminate the need for expensive raw materials and or minimize waste problems. Phase transfer catalysts are especially useful in green chemistry by allowing the use of water. The need for organic solvents is reduced. Here I am showing the light switching crown ether. Since these ligands can imitate some biologically occurring natural compounds, they are expected to provide insight into the biological phenomena occurring in living systems. For example, the mechanism of the sodium pump occurring across a cell membrane could be understood using the formation of the alkali metal crown complex mechanism as a model. I am ending now my presentation.